So let's get on with the show. Professor Paul Kwiat, his area of expertise and research is quantum information and quantum optics. In fact, he gave us a Saturday physics lecture, was that 2 years ago or 2 years ago, on quantum mechanics. It was just fascinating. This year, he was organizing the Science Olympiad that was here, the National Science Olympiad that was here on campus. And as part of that, for World Year of Physics, he gave a talk about Einstein. And it was incredibly well received, so we were more than happy to have him reprise that talk for us here today. He's won numerous awards, and he's just world-renowned for his research, and so I'm not going to go into a long list of awards. You actually can click a link to a web page that will describe all of that for you. But he's, in addition, a very gifted teacher, and he's very good at relaying a lot of kind of advanced concepts to everyday people like you and me. And so I'm really excited to hear this talk about one of the greatest physicists in the history of all of mankind. And so without any further ado, help me welcome Professor Paul Kwiat to tell us about Einstein.
Thanks very much, Kevin. Yeah, that is a good name. So as I get suited up here, I'll just have you guys look at some other famous Einstein quotes. He definitely knew good ways to put things, and he was a fun guy as well. Okay, so now I just have to keep track of all the different computers that I have running at one time. Okay, so let's stop this. No, wrong computer. Let's stop this. Let's stop this. Let's open this. Let's start this. Okay, so I want to talk about 100 years ago, 1905, which really is not very long ago if you think about it in terms of, the history of civilization or something like that. It's actually very, very recent. And what an amazing year it was. And basically, physics completely turned around, not exactly on that year, but if you had to pick one year where old physics became new physics, it sort of happened more or less in that year. If you had to pick one year, that would be the year that you would pick. And remarkably, it was all due to one person, Albert Einstein. And it was due to 3 ideas that he expressed, or that he brought forth in that year in 5 different papers. This is why it's a trilogy in 5 parts. And so that's what I want to talk about today. And I hope to convince you of a number of things. I hope to convince you that Einstein was really a very, very, very smart individual. Not smart just in terms of being able to do lots of equations, but really smart in terms of being able to look at things in a totally different way and to break free from the establishment at the time. And the second thing is I hope that you'll walk away with some understanding of what those basic ideas, these sort of 3 main ideas that he introduced in that year was, and what effect they had on physics then, and what effect they have on life now, because they have a huge effect on all of our society, all of our technology and techniques. So this is, of course, only for you. It's not for me. And so if you have questions, you should just ask questions as we go. That'll be the best thing. And I'm going to be asking you questions as we go anyway, and you should answer them, or try to answer them. And if you give wrong answers, that's even better, because it means then we can all learn something. If you always gave the right answer to every question, that would be boring, because it would mean you already knew everything. Okay, so, not this keyboard, this keyboard. So 2005 is the World Year of Physics, and the reason, as I mentioned, is that it was in that year that Einstein published 5 papers on 3 topics. One of them was on describing Brownian motion, which connected thermal physics and statistical mechanics, and we'll talk about all of these. One of them was on special relativity, which showed that our prior conceptions of space and time were totally different than what we had thought they would be. They weren't absolute. They became relative quantities. And the final idea had to do with the fact that light is not some continuous thing, but actually comes in little packets, which we now call photons. And that basically started the whole field of quantum mechanics, which I like because it pays my rent. Okay, so question. For which of these, for any of these, did Einstein get a Nobel Prize in 1921? He did get a Nobel Prize in 1921. The question is, for what topic? Was it any of these or something else? Does anyone want to hazard a guess who doesn't know the answer? Obviously, if you know the answer, then you know the answer. Somebody who thinks they know the answer, but they're not sure. Yes? Relativity. That is the #1 choice. But survey says, Okay, so most people think it was for relativity because that's what he's most well known for. But actually, it was for this idea. It was for the photoelectric effect, and we'll explain what that's all about, which was then seen as a proof of the existence of the fact that light comes in these particles that we call photons. And in fact, a couple years after he made his predictions, then actually a number of years, Robert Millikan performed a definitive set of experiments, and then Millikan got the Nobel Prize in 1923. Okay, so lots of Nobel Prizes. People weren't so comfortable with the idea of special relativity at the time, and that's why he didn't get it for that. There was a huge discussion of whether he should get it for that. So I'm going to put up a number of quotes as we go for Einstein, and hopefully I can tie them in. Give you guys a chance to catch up and give me a chance to open my notes so I see what I'm supposed to say here. Okay, so Einstein was really big into having sort of a vision, a deep understanding of things, and not to just sort of accept things and say, yeah, okay, that's fine, that's the way the world is, but to really try and understand why it is that way, how it could be that way. And that was how he gained a deeper appreciation for nature and for the world. He also said that we should try and make things as simple as possible, but not any simpler. I will try to do that here. To any physics colleagues here, I apologize. I might end up making them a little simpler than they should be, but we'll see how that goes. I think I'm going to tell mostly a true story here. Okay, so Einstein was famous because, one of the things that he introduced was this notion. Let's see if I can get back here. Let's see. Oh, I can hide. If I get shy, I can just hide away. He introduced this notion of he was famous for a Gedanken Experiment. This is a German word for thought, a thought experiment where you could just get some information, some insight about something just by thinking without actually having to go out and do an experiment. So I want to start with our first Gedanken experiment here, and that's that you're sitting by the pool and you're dipping one toe in the water of the pool, sort of periodically putting a toe in the water of the pool. So you can kind of all imagine what's going to happen. What are you going to see in the pool? I'm going to see some sort of rings going out from my toe going in the water. That's right. And if instead I do it with both toes, well, I'm going to get double sets of rings going out. And I will see, so I'll have these waves from the water. So this is what I'm trying to get at. I want to come to an understanding of what the state of the knowledge was when Einstein was starting to think about some of these things. And so if we put our toe in water, we drop something in water, we get these waves that come out from wherever I touch the water. And if I do that with two sources like this, then I will get places where the crests from one wave hit the crest of another wave, and I get a very high crest, and places where the crests hit the trough and things cancel out. So I will get constructive and destructive interference, and I can demonstrate that here. I actually have a couple demonstrations of it. So one of them is just with this, I have a tank here that's filled with water, okay? And I have a little device that's just going to put two toes in the water repeatedly. Okay, and we can see that there are places where there's sort of really big crests and deep troughs. That's where things are constructively interfering. And we can see that there are places where they're sort of canceling each other out. So they're canceling each other out here. They're canceling each other out here. But here there's a lot of action. Here there's a lot of action. Here there's a lot of action. So this phenomenon of interference is the key feature of something acting like a wave. Okay, let's do another example of that. So I have to switch computers back to this computer. And I'm going to get rid of this. I'm going to get rid of this. Okay, so what I have here is just a computer program that's simulating what we've just seen with the water waves, where I have the two sources going in, and you can see the light and the dark patterns. And I can change, for example, the frequency of the waves, and then the patterns get bigger if it's a lower frequency, and they get smaller if it's a higher frequency. And some of you may have seen this same sort of a demonstration with these Moray patterns, where I just have, if I have a bunch of concentric circles here and I bring in another source like this, as I bring them together, well, now I can see these sort of interferences where I'm getting constructive interference, say, along this direction, and destructive interference, say, along these diagonal directions. But interference is actually something that you can really experience directly. You can actually hear it, and that's what I want to do now. There's this great little demo, which, if I turn this on again, so what I'm going to do is put some sound onto the two speakers. There's a speaker here and there's a speaker here. I'm just going to play a tone, and this is what the interference from those sound waves looks like in the room. Something like that. And maybe I'll change the frequency a little bit. And I'm going to turn this on, and you notice that there are places where it's constructive, places where it's destructive. In fact, if I give us a bigger view of this, you can sort of see here are the two sources, and here are these. Here's where it's going to be loud, soft, loud, soft. And if you just put your finger over one ear and move your head from side to side, you're going to be able to go from one of these loud places to one of these soft places. People hear it. So this is what's happening if you're in a room that has good acoustics or bad acoustics. It has to do with partly with whether or not you're getting these destructive interferences taking places where the room is really dead. I can also do this with a different frequency if I lower the frequency. I'm going to have to move the head a lot more in order to go from one. This is cool. It's kind of like Stevie Wonder or something like that. Okay, so interference is a real thing. And it proves that we have waves. Okay, well, the question then is light a particle or a wave? And back in the late 1600s, Isaac Newton more or less proved to his satisfaction, and in fact to everybody else's satisfaction, that light was really made up of its particles. It was made up of corpuscles. And so that was the end of the story, because people believed Newton because he was a smart guy, and so light was made up of particles, and that was it. However, in the early 1800s, the French Academy was having a science competition, and one of the entrants was Fresnel. Whoop. Okay, how come none of my lights are working? All of the light switches seem to be defunct. Is someone actually like leaning on a light switch upstairs? There we go. Okay, so no leaning on the light switches. Okay, so yes, we were talking about light, exactly. So one of the entrants, Fresnel, who was a young mathematician at the time, he thought that light should display diffraction just like sound should display interference just like sound does. And one of the judges, Poisson, who was a very well-known mathematician at the time, he knew that light was made of particles, and he came up with an argument that showed that Fresnel's idea must be absolutely ridiculous. And the argument went like this. Let's see. I need to raise this just a little bit. So Fresnel, well, Poisson said if light is a wave that's coming in, and if I have some sort of a black object here, then normally, of course, what you'd see is you'd see on some screen over here, you'd see some light over here, for example, and you'd see light over here, and then there'd be this region that's in shadow. Fine. That's like if you imagine throwing particles at this thing. But if instead you imagine that this is a wave, well, we've seen what happens with water waves. I mean, the water waves curve when they go around objects, right? So the waves start to curve a little bit. And if I imagine my waves coming through here, because they're supposed to be sort of equally spaced, the distance to get from here to here is going to be the same as the distance to get from here to here. So that means that the waves are going to come in phase. The crests are going to come on top of the crests. The troughs are going to come on top of the troughs. And in fact, I have a demonstration of that as well. At least I do if I didn't get rid of it, which I did. So give me just 1 second. Okay, so now I'm going to put an obstacle here. So here's my obstacle, and we see that if I have waves coming in, then I expect to see behind the obstacle, although there is this kind of dark regions, but there's this bright spot behind an obstacle. So what Croissant was saying then is that if Fresnel was right, if light was really a wave, then if I were to look behind a black object, if I were to have a small opaque object and shine light on it, that I should see a shadow, but I should also see a bright spot right in the middle, and that's totally absurd because, of course, you would never see that. So Croissant was a theorist, a theoretician. So he didn't actually even need to do the experiment. He knew that it was absurd. Fortunately, one of the other judges, Arago, was an experimentalist, and he thought, well, why don't we actually do the experiment before we make a decision about this? So we're going to do the experiment here. I just need to switch. Okay. Okay, so what I have here is just a green laser, which is shining on a screen, in which you're seeing a camera here. And what I'm going to do is put in front of this a little ball bearing, and the ball bearing is acting like this object. And when I do that, we get the shadow, but right in the middle of the shadow there's this bright spot. It's often called the Croissant Spot, which is really kind of unfortunate because Fresnel is really the one who proposed the whole thing. I don't know, it should be somehow the Fresnel-Croissant-Arago spot or something like that, but no one says that. So, okay, so we've got this interference of light. We've got this bright spot in the middle. If you think about throwing particles at this object, so if here's my object and I think about throwing things, there's no way that I'm going to get them to have a bright spot right behind the object. There's just no way that that could happen. So that means light must be a wave. Okay, so this is what people now know at this stage. Light is a wave. And, well, the next question is, what is the light actually waving in? So every other time we had something waving, like when we have water waves, the water was the medium that was carrying the wave. Or when we had sound waves, it's the air that was the medium that was carrying the wave. Or if we had vibrations going through, going through a piece of wood or a piece of plastic, it's the material that's carrying the wave. So up until now, we've always needed something to carry the wave. So now I've got these light waves. There must be something that's carrying those waves. And that was thought to be known as the ether. It was kind of a strange material because, well, people knew that the speed of light was really fast. Okay, and let's see, do people know, does light go faster in a solid or in air? If you put your, let's see, if there's a loud bang off somewhere, are you going to hear it sooner if you hear it coming through the air or if you put your head on the ground? It turns out it'll actually go faster if it's going through a solid, and the reason is that in the air, for the sound to propagate, the air molecules have to move a while till they bump into another one, and then they have to move till they bump into another one. In the solid, in some sense, that also happens, but they're all locked together in this rigid lattice, and so as soon as one of them moves, the other ones start to move, and so you get a much quicker propagation. So things are going to propagate, sound will propagate faster through a stiffer material. Now we have light that's propagating, and it's propagating faster than anything else that people know. It's propagating at 3 times 10 to the 8th meters per second, so very, very, very fast. So you think that you need something really, really stiff. This ether must be this really stiff thing, and yet the Earth, we know, is going around the sun, and even the sun is moving in our galaxy, and the galaxy is moving, and so we must be moving through the ether, and so somehow it's weird that we're not feeling the effects of this ether. Okay, so we need to be able to, we want to do an experiment to test, or people wanted to do an experiment to test if there is an ether, and the idea is that if there's this ether that something is propagating in, that light is propagating in, then it should depend which way the light is going. So if the ether is going one way, it's sort of like fish in a stream. If the fish are swimming with the stream, they're going to go faster. If the fish are going against the stream, they're going to go slower. So the light should behave the same way if it's going through the ether. Okay, so now we need some sensitive way to compare speeds, and this is a device called an interferometer, and I have another picture and a demo of this. Okay, so we're done with this, and we're done with this. Okay, so what I have here, and then I'll do the actual demo in a minute, is I have a little light source, and I'm going to have a pulse of light which is going to come off. It's going to hit this. What is this? This is a half silvered mirror. So this is going to let half of the light be transmitted, and it's going to reflect half the light. These are perfect mirrors, so the light's going to say either come this way, bounce off this mirror, and then again it could either go this way or this way. Let's say that it comes down. So the light could either come this way, or the light could come this way, and we will be able to time basically how long it took to go one path as opposed to going the other path. So in this case, if the path lengths are the same distance, it takes the same amount of time to reach these end mirrors and then to turn around and come back, and these two parts of the pulse line up exactly, and that leads to constructive interference in this case. So just to tie this in what we've already seen. Okay, so I actually have such a device over here, and I just need to switch the camera so you can see the output. So what I have here is exactly what's on the screen. I have a laser that's shining here, and I have a little beam splitter here. That's this thing. And then the light can either go straight through to this mirror, or it can be reflected to this mirror. And then when they come out and I look on the screen over here, I get this pattern. Now, I will change from having this is a very sensitive measure, because I'll be able to change from a light to a dark. I'll be able to change from constructive interference to destructive. All I need to do is to shift the two waves which are coming together. If I shift them so that the crests don't overlap, but instead the crests overlap the troughs, then I'll go from constructive to destructive interference. Okay, but the wavelength of light, the distance from a crest to a crest, is very short. It's about 1/100th the diameter of a hair. It's about half of a micron. So this is an extremely sensitive measure of whether things are coming together at the same time. In fact, I need a volunteer from the audience. What's your name? Jared. Jared? Yeah. Okay, Jared. So you look like a big, strong guy. Good. Okay, so I want you to touch this mirror, and I want you to make it so that instead of it's being light in the middle, it's just dark in the middle. Whoop. Okay, so that was what I said to do, which is not what I should have said to do. We're going to try this one more time once I get this going again. So I'll give you a hint, which is that you have to press not quite as hard as you pressed. In fact, quite a bit more gently.
Just press like that.
Yeah, I would try pressing as gently as you can. Whoop, more gently. More gently. No, more gently. Here, maybe this will help. Sometimes it can help if you just press with a little tissue on this. Okay, so I'm barely pressing at all to make it move. It's really, really sensitive. Any of you can come up afterward and see that it's basically an impossible task. He's only got to move that mirror to go from light to dark. It turns out 100 nanometers. That's about 1/1000th the diameter of a hair. Okay, so it's extremely sensitive. So it's basically an impossible task. You did very well in an impossible task. Thank you. And just for helping us out in this impossible task.
Thanks.
Okay, so this is an extremely sensitive way of measuring whether or not light is going to be going slower or faster. Let me show you if indeed there is, for example, there's an ether here. So here's this ether which is flowing upstream. And now if I run this experiment, well, we'll see what happens. Now the two don't come back together anymore, because it helps you to be swimming upstream, but it hurts you more to be swimming downstream because you're there a little bit longer, because it takes you longer to go the same distance. Okay, so this is a device then which is sensitive to whether or not there's an ether, and the way that you test it, because you don't know, maybe there's an ether in this picture which is going at, I'm not going to try and set this way, but maybe if instead the ether was going at a diagonal, then it wouldn't cause any difference. So you need to rotate your whole interferometer to see if you get any difference, and that's just what Michelson and Morley did. They're from Michelson-Morley experiment was done in Cleveland, Ohio. One of the only good things to come out. No, I'm from Cleveland, Ohio. So street lights also came from Cleveland, Ohio. So any traffic jams you can blame on the Clevelanders. So the idea was that they could rotate this very sensitively, very gently, and they could see whether or not the pattern shifted. Now, I'm not doing this very gently because I'm on a very bumpy floor and this thing is not very isolated. They actually had a big interferometer that was floating on mercury, and then they could just rotate the whole thing without having any vibrations. And they saw nothing. They got a null result. They did not see any dependence on how the interferometer was oriented. So the conclusion then was that the speed of light was the same in every direction. So there was no ether. Okay, so that was kind of strange. So people didn't really know what light was propagating in then. Okay, so now Einstein comes on the scene, and he was a young Einstein at the age of 19 and was troubled. And he was troubled by a paradox, which I'm going to call the mirror paradox. So Einstein said, let's say that I'm looking at my face in a mirror. Well, actually, maybe I should first recall to us a little bit more basic understanding, which is that in general, according to Galileo and according to Newton, velocities will add or subtract. So for example, if I can throw this tennis ball at 10 meters a second, fine, I can throw it at 10 meters a second. If I happen to be at the same time on a skateboard going at 2 meters a second, and I throw this at 10 meters a second, then how fast is the ball going to be going? 12 meters a second, right? There's no question that that's the right answer. Okay, so velocities add in that way. So here was Einstein's paradox. He said, well, light is going always, light is, has this fast speed, and it doesn't matter what direction it's going. It has this very fast speed. So the question is, if I have my mirror, which is sitting over here now, and I look at my face in the mirror, what happens if I'm moving with the mirror at the speed of light? Okay, so in other words, so here I am. Here's this mirror that I'm holding in my hand. And in order to see myself, I have light which is bouncing off my face. So some coming in, bouncing off my face, hitting the mirror, and then bouncing back into my eye. And so the question is, if I'm moving, if this whole thing is now moving at the speed of light, what's going to happen? Now, it seemed like there were two possibilities. One possibility is that when I get to moving at the speed of light, the light itself, which I'm going to at the moment say is represented by this ball, the light can't actually catch up to the mirror because the mirror is moving at the speed of light. And therefore, at some point, if I'm moving at the speed of light, I won't see my reflection anymore because the light never makes it to the mirror to bounce off and hit my face. So my reflection will disappear. The other possibility is that instead, this is moving at 3 times 10 to the 8th meters per second. Okay, c, the speed of light is equal to 3 times 10 to the 8th meters per second. And if the car is also moving at 3 times 10 to the 8th meters per second, then that's fine, except that if someone were on the ground watching this happen, then they would see the light moving at, let's see, 3 times 10 to the 8th meters per second plus 3 times 10 to the 8th meters per second, or twice the speed of light. So they would see things moving faster than c. Okay, so Einstein was troubled by this paradox. And in particular, there was one principle that people believed, which is that you shouldn't be able to tell if you're moving. That seems like a strange thing, because of course you can tell if you're moving. But if you're, for example, in an airplane and you've fallen asleep and you wake up suddenly, you don't necessarily know just from sitting there whether the airplane is on the runway or whether it's flying through the air. Unless you look out the window and you see that things are moving by, then you can tell you're moving. But if you're in a closed system, there shouldn't be any way that you can tell that you're moving. And so according to this mirror paradox, then, if in fact the light couldn't catch up with the mirror, then you could tell that you were moving, because if you weren't moving, you could see your reflection. If you're moving at the speed of light, you wouldn't see your reflection anymore. Okay, so Einstein then came up with a resolution to this seeming paradox, and the resolution had two postulates. One of them was that what I've just said, the laws of physics are the same in every inertial frame. That means frames that are either stationary or moving over the constant velocity, constant speed, so that if you perform an experiment on a train going east or on a train that's stationary or a train that's going west, you always get the same results. So that was the first assumption that he made. And the second assumption was that the speed of light is the same for everyone. It doesn't matter if you're moving or if you're not moving. Everyone will always have the same speed of light. Okay, that's a little bit of a strange thing. And the reason I say that that's strange is that according to Newton and according to Galileo, we would have said that the speed of light is something, or the speed of something moving can change depending on whether or not the person's moving or the observer's moving. So like I said, if I'm on a skateboard and I throw this, it's going to be going faster than if I'm not on a skateboard. Einstein instead said, no, the speed of light is the absolute. That's the thing that you're not going to change. But in order to get everything to work out, it's going to have to be the case that what we mean by space and time themselves are going to have to change. They're not going to be constant like they were for Galileo and for Newton. Things are going to change. Now, one of the things that's going to change, for example, is simultaneity. So simultaneity is when we say, two things happen at the same time. So, for example, right, okay, yes, so I get the same measurement of C no matter how I make the measurement. So this is a cartoon I had up at the beginning. So we notice that Einstein and Edison are pretty close in their points here, and maybe that's because there were a lot of cases where they were both hitting the button at more or less the same time, being able to answer. And so there's a sense of simultaneity, although one of them maybe comes first. So simultaneity says that, okay, if I drop these two things, they hit at the same time. And it seems very reasonable that if I see them hitting at the same time, then if you were on a skateboard going by, you would also agree that they hit at the same time. That's a very natural kind of thing, that simultaneity shouldn't depend on who's looking, on whether the person is looking, is moving or not moving. But we're going to see now that that's not the case. That's really wrong. That really basic notion of how things are connected in time and in space is wrong. And here's the idea. So I have this girl, Alice, is on a spaceship, and she's got a little flashing device at the middle, and when she hits her button, this goes flash, and then light goes out in all directions. And it's going at speed c in this direction, and speed c in this direction, and speed c in all directions. And she's got two detectors on the ends of her ship. And if she's right in the middle of her ship, what can you say about these two detectors? How are they going to fire? Well, they're going to fire at the same time, right? Because the light is going off at equal speeds, and it's going to reach both detectors at the same time, and they're both going to go click at the same time. Let's say, how would this look, though, from the perspective of someone who is standing on the ground watching this happen? Okay, so Alice has hit her button, and the speed of light, the photons are going off at speed c. But now from the perspective of this guy who's on the ground, because her ship is moving forward in some direction, the light is going to hit the back of the ship before it manages to catch up to the front of the ship, because the front of the ship is running away from the light and the back of the ship is running toward the light, and so the light has to go a shorter distance to get to the back of the ship than it has to go to the front of the ship. So according to the guy who's standing here, they don't happen at the same time. The back one goes first, and then the front one goes first. That's really different. That's really very, very different than the normal notion, which is that no matter how you're moving, everything will happen at the same time. Okay, so this whole notion of simultaneity was sort of thrown out the window. Okay, the next example is this thing called time dilation. So let's talk about that. So if you want to make a clock, there are a lot of ways that one can make a clock. One way, we have all these digital watches and things like that, or you could imagine having a pendulum. I'm going to describe sort of a different kind of clock. So a clock where I'm just going to throw this up, and I'm just going to catch it and if I throw it once a second, well, okay, how do I know what once a second is? If I throw it equally hard each time, then that is a clock, right? Now, I don't want to do this with a tennis ball because there's nothing absolute about tennis balls, but the speed of light is absolute. So if instead I do this with light pulses, then I can get a little bit more information. So, okay, I can close this. Okay, so here's the same thing. I'm going to have two people, and one of them is, they're both throwing up light pulses. They're bouncing light off the ceiling and waiting for it to come back down, and that's a light pulse, and that's going to be one click of their clock. And if they're sitting next to each other, notice, oh, the light comes up at the same speed, it hits the mirror, it comes back down, and then they agree. Okay, so their clocks are in sync with each other. Their clocks are beating at the same rate. If, on the other hand, one of the clocks is moving, so in this case the blue clock is moving, remember the speed of light, this is one of the assumptions, the speed of light is the same no matter whether you're moving or you're not moving. So these particles are moving at the same speed, but from the perspective of the red guy looking at the blue guy, the light has had to go this longer distance. It hasn't had to just go up and down, it's had to go a longer distance. And so therefore, for the person, the red person looking at the blue person moving by, the blue person's clocks, there's a longer time between clicks. So the blue person's clocks are running more slowly. So I have these two clocks, and normally you would think that it doesn't matter if clocks are moving, time is still going to be the same. But now what I'm saying is that if instead I have a clock which is moving, a moving clock is going to run more slowly. And it doesn't matter what kind of clock. It's not so much that the clock is running more slowly, it's that time is different for this moving frame than it is for the frame which is stationary. So it holds for every possible kind of clock that you could imagine. Okay, it's actually pretty easy to show how much it's, what the difference is. I'm just going to write this up. I'm not going to try and show it, but it's actually a very easy. Well, maybe I'll just indicate a little bit how it would go, in the sense that if normally you have to go this distance, and instead you have to go this distance, so this distance, it's a real simple application of Pythagorean theorem about how much longer this is than this, and this is how far you can go if you're traveling at some speed v for some time t. So you can work out from Pythagorean theorem, and it's easy to show then that t, the time that I see a moving clock, is equal to the original time times 1 over the square root of 1 minus v squared over c squared. So if v is very, very small compared to the speed of light, if the velocity of the moving clock is small compared to the speed of light, this looks like 0 and this looks like 1, and then the two things agree. But if instead you're moving fast compared to the speed of light, then this thing becomes closer to 0 and this whole thing becomes bigger. Then t prime becomes bigger than t. Okay, so a moving clock apparently runs slower than a clock that's not moving. That's very strange. As an example, let's say that I take me running. So I'm running along at 1 meter a second. Figure out how much time I save, how much time off my life, since my body is not aging as quickly in that case. So if I'm running at 3 meters a second for 30 years, it turns out that I'll be younger by about 1/10 of a microsecond. Okay, so not a really big effect. Now, there still might be reasons to run every day, but not running constantly for 3 meters a second for 30 years. It doesn't buy you much from a relativistic point of view. Okay, there are particles that are born in the upper atmosphere when cosmic rays come in, called muons. A muon is like a heavy electron. And if you have a muon that's sitting still, it won't last for very long. It lives for about 2 microseconds, and then it decays into some other particles. If instead it's moving, which they are when they're born in the upper atmosphere, they're moving very fast. Instead, they live something like 14 microseconds. I bring up the muon experiment just because that was one of the first key experiments that proved that Einstein's predictions were perfectly correct in this. The GPS, global positioning satellites, which are becoming more and more a part of our lives, knowing where we are on the planet, they have to use relativistic correction. If they don't take into account the fact that because the satellites are moving, they're going more slowly, they get off about a tenth of a microsecond a day. Now that might not seem like a long time, but that corresponds to about 30 meters error a day. And so if you were to go for a whole year without taking that into account, you'd be off by 30 meters times 365. So you'd be way off. You'd be in the wrong place entirely. So this is absolutely a verified thing. The moving clocks actually run more slowly than clocks that aren't moving. Let me ask, are there any questions at this stage? I've kind of been rambling on, but okay. Another consequence of this of relativity is that when objects are moving, they look shorter. So for example, if I have these two ruler kind of like thingies, they're not really meter sticks and they're not really rulers, but anyway, these two measuring devices, and one of them is moving with respect to the other one, then the moving one is going to look shorter to me. It's going to look like it's compressed. And that's also actually really easy to show. It takes a little bit of trigonometry, and actually it's easiest to show by using an interferometer like we had over there. It's a nice simple argument. And if this were just a talk on special relativity, then I would just go and I would show that to you, and you'd see that it's just a little bit of algebra. So it's really not any complicated kind of math. So the effect is small if you're not moving fast with respect to the speed of light, but as you get faster compared to the speed of light, then the effect becomes more and more compressed. Things look shorter and shorter. Okay, this is a so a few months after he published his paper on relativity, Einstein then came up with a consequence of relativity, and I'm not going to try and derive that here, although it's actually very simple. The paper is only a couple pages long. It's very simple. And the consequence is this very famous equation, the E equals mc squared. So the relevance of this is saying that energy, basically energy and mass are equivalent if you multiply by this constant c squared. C, of course, is a big number, so c squared is an even bigger number, so a little mass goes a long way in terms of energy. So the consequence of this is that we can convert and interconvert mass into energy. And that, of course, is critical. I mean, this is always true. It becomes very manifest when we think about nuclear power or nuclear weapons. In both of those cases, we have some substances which initially start out heavy, and then in the process of, say, breaking them apart, they're a little bit lighter than when they were together. So they were a little bit heavier when they were together. They're a little bit lighter now, and that extra mass has gone into the energy, which then goes into kinetic energy, and then which either powers plants or weapons in this case. Another consequence of this, actually maybe before I do this one, you guys all know from, so people actually know this now intuitively. It's in our society. Of course, people know E equals mc squared, but people know what happens when the matter and the antimatter drives on the Enterprise come close to each other, right? That's always a bad thing because the whole place is going to blow up. And so this is true when we have particles like electrons and the negative, and the opposite charge of that, the positron. When they come together, they completely annihilate, and then they turn into light. They turn into two photons that come flying off. Similarly, if you have a lot of electromagnetic energy, a lot of light energy, it can sort of spontaneously convert into pairs of particles or more particles that just come shooting off. So we can have this interconversion between mass and energy. One of the consequences of this is that, and here's where I'm going to use a little bit of a simpler description, the momentum increases with speed in sort of a strange way, and we can interpret this as the effective mass increases with speed. So as I try and move something, as I'm trying to move this tennis ball, the faster I move it, effectively it's that it's getting heavier and heavier. It's getting more and more massive, and so it becomes harder and harder. I have to put more and more energy to get it to go a little bit faster, and then even more energy to get it to go a little bit faster, and so you can never actually get a massive particle up to speed c. This is not so good for a space program, but nevertheless, that is a consequence of this thing of Einstein's. Okay. So I'm going to change gears entirely now. So we've finished now one of the three main ideas. The next one, and I did that in some detail just because it's fun and relativity is a cool thing. The next thing I want to discuss is Brownian motion and what is this all about. So I have another demo, although I might have to get it set up again. 6 both. Okay, no, we can still see it. So what I have here is a little cell, a little glass cell. And what I have done to that cell is put a little smoke in it, some smoke particles. And now we're shining light into it. And the light is scattering off the smoke particles. And if you just sort of look at one of them, I mean, there's a general flow. And the reason there's a flow is that the lamp is heating the air, and then that's causing some circulation. But even if I move to focusing on a different place, we can sort of move that away. If I just look at this, if I look at one of these particles, you can sort of see, it's a little hard to, maybe if I turn the lights off, it'll be easier. It looks like they're sort of moving, they're jittering around a little bit. I mean, they don't necessarily stay in focus for a huge amount of time, but I'm hoping you can see a little bit that they look like they have some kind of random motion. And again, if I move to maybe a little bit higher up. So there's a net drift, but you can definitely see that they're sort of wiggling left and right or top to bottom as they're going through here. Okay, so that's similar to, that's in some sense an example of this thing called Brownian motion. So Robert Brown was a botanist who in 1828 noticed that if he had a microscope and he had some pollen in water, that the pollen seeds, these are very, very tiny seeds, they seem to move in kind of erratic patterns. And initially people thought that they were actually living entities and that they were somehow swimming. And then he was able to show that no, it also works if you take little sand particles, and any kind of little particle will undergo this kind of random motion. And no one could really explain what was going on there. And then Einstein said, well, okay, I think I know what's happening. So at the time, people did not yet know, people were not sure that there were atoms at all. We all know now that there are atoms and that there are other molecules, so this is so totally obvious to us that it seems weird that there would ever be a time when people didn't know that. But back in the early 1900s, it had been suggested, but certainly had not been proved at the time that there were molecules, and people didn't necessarily believe that there were. And Einstein said, well, I think I can explain this in terms of molecules. And I have another demo of this. At least I think I do. Brownian motion. There we go. So let's reset this. So here's what you see in your microscope. You see this pollen molecule that looks like it's doing this sort of arbitrary walk. But what's actually happening, according to Einstein on a microscopic scale, is that the molecules of the water are bumping at random into this thing, and they're causing it to do this sort of a random walk through. And that's causing the particles to move, again, in this kind of random way. Now, one of the other things that Einstein did in his paper, because he really wanted to prove, he wanted to have a definite proof that that there were molecules, so people would actually believe it, that there were water molecules. And in the past, people had tried some things to try and detect this. One of the things they tried to do was try and measure exactly the trajectory of this pollen molecule. Now, this is kind of slowed down here so that you can watch it. But if you imagine trying to take these smoke particles and map exactly what the trajectory is, you see that it's not very easy because they don't appear for very long. Or you might try and, say, map how fast they're moving at any given time. But again, that's a very difficult measurement. So Einstein instead had a different suggestion. He said, let's look at basically how far they diffuse, how far they move out as a function of time. I just want to know on average how far they're going to diffuse out. And he came up with a definite prediction. And in fact, we can see this prediction here. Let's see, I need to go back to that. Close this. Move this down. Clean my finger because I put it in glycerin. Okay, so what I have here is a container that has some glycerin in it, so just heavy water, as it were. You could do this with normal water, but it happens too quickly, so it's a little hard to see. And then I'm just going to put a ruler under this. So we've got a zero point here. And now I'm just going to put some long molecules into it, some dye molecules, long dye molecules, green food coloring. And what we're going to watch is when I put it in, this is going to expand in a ring, but sort of exactly the speed at which it expands is the key, or the way at which it expands is what we want to look at. Okay, so you can track this outer ring. So let's say I had done this with a stopwatch, and I've done this before. And you measure, okay, here's when it gets out to 1 centimeter. And now I'm going to see how long it takes to get out to, from the other, say, 1 centimeter, how long it takes to get to 2 centimeters, how long it takes to get to 4 centimeters. And you write all those things down. What you will find is that the time that it, basically the displacement that you go, the average displacement, goes as the square of the time. It doesn't go linearly with the time. It goes as the square of the time. So if you want to go twice as far, you have to wait 4 times as long to diffuse out. It's a general phenomenon. And this is basically what Einstein had told the experimentalists that they should try and measure. And Einstein was able to predict exactly how long it should take for these things to expand and for things to move, depending on how big the atoms were, or how big he thought the atoms were. No one had actually seen molecules directly at that time. Okay, so he was able to predict, to explain this random motion and to make definite predictions. And those predictions were then verified by a French chemist, Jean Perrin, a few years later. And that basically finally confirmed the kinetic theory, confirmed that atoms existed. And then everyone finally accepted it. And then there wasn't this controversy anymore about whether or not there were atoms. So as I've said, the distance goes like the, I'm sorry, I got it backwards, goes like the square root of the time. Right, to go twice as far takes 4 times as long, so I did say that right. So this is not maybe the most, what do I want to say, sexy of Einstein's predictions. It doesn't have anything to do with space-time being all altered or things that, quantum mechanics coming in. Nevertheless, it's really critical for all kinds of things in our lives right now. When you make electronic devices, you rely on this diffusion to create these things. Inside our biological cells, the way that the chemicals, neurotransmitters gets from outside of the cell to inside the cell is by a diffusion process. Whenever we have flow of heat going through any kind of, going through liquids or solids, that's relying on that in chemical reactions. So this is actually, these papers of Einstein's on particle diffusion are the most cited of his, I think are some of the most cited of his papers. Okay. Now we're going to turn to the last of his ideas, which is the one that he thought was really the only revolutionary one. So only one of them was revolutionary. And this is this notion that light actually comes in particles. And this is he examined this with the so-called photoelectric effect. So what is the photoelectric effect? So we can do another demo with this. Okay, so if I have a piece of metal, so I have some piece of metal here. We all know that metal has electrons in it. That's, that's given now. We know it has electrons because it can carry current. The electrons are also, they're bound inside the metal. Okay, so they don't just spontaneously leave the metal. How do we know that's true? How do I know that the electrons in my thing aren't just spontaneously leaving? Yes? Because the metal remains together. The whole thing just doesn't dissolve. Perfect. That's exactly exactly what I wanted. So if the electron does leave, it would leave behind a net positive charge, and then it would be attracted back to that positive charge. So the electron, in some sense, is sort of bound within the metal in this case. And we need to, it is possible to release it, and one of the ways that it's possible to get the electron to come off the metal is that you can shine light onto the metal, and then it's possible to get an electron coming out. Okay, so I can shoot off an electron. So I want to demonstrate, so I'm stating to you that that's the case, but let's actually prove to you that that's the case. And to do that, I have another demo over here, and it is using a, let's see, what can I, maybe I'll move down here this time. It's using an electroscope, which is a cool device. So I have a device that has a big metal ball, and then it's connected by a metal tube to some gold leaves. And I'm going to start out by putting some electrons on this metal ball. And what's going to happen is the electrons, they're like charges, so they repel each other. They don't want to stay right next to each other, so they're going to redistribute themselves. They're going to run down to the ends of these foils. And then because they have the same charge, the foils are going to separate because like charges repel. I'm sort of assuming that people know this back from elementary school or something like that. So the charges are going to be repelling. And now what I'm going to do is then shine on this. There's a metal plate here, and I'm going to shine light on this thing. And if what I say is wrong, then shining the light's not going to do anything, and these foils are going to stay apart. And if what I say is correct, then when I shine the light on it, it's going to shoot off electrons. And therefore, there aren't going to be as many electrons up here. And therefore, these electrons are going to be able to run back up here. And then the two leaves are going to come together. Yeah? Does that make sense? So if the leaves stay apart, it means that the electrons are still staying on the top of this thing. And if the leaves come together, it means that I'm somehow knocking electrons off. OK, so what we have here are the two. There's one gold foil and the other gold foil. Because there's a lens in here, it's inverted, so they're actually hanging down, but they show up like they're hanging up here. And I'm just going to put some electrons. Oh, thank you very much. Put some electrons on this. OK, so now these are definitely charged. OK, they're staying apart from each other. If I turn on this nice bright lamp, though, now we see that they're coming together. And if instead I block the bright lamp, then they stop coming together. And when I unblock it, then they finish coming together. OK, so this is the photoelectric effect that shows that as I have a bright light on the thing, that things are going to move together. And now the question is, well, how do we understand that in terms of the fact that light is a wave? Because we know that light is a wave, so what does that mean when light is a wave? And there are a couple of predictions that you could make on the basis of the fact that light is acting like a wave. One prediction is that as I make a brighter light, I should get more current. Another prediction is that if I have a very weak light on it, it will take me a while to get enough energy to actually release the electron. And so I have a sort of a classical demo of that. Here's my physicist model of the electron inside the material. And I'm going to say that the electron is free when the electron takes off. And so here I'm pouring in a little bit of light at a very low rate, a very weak light. And notice it takes time to get enough so that it actually takes off. So there's some time delay when I put the light in. That's if light is a wave. The other things that we expect is that changing the frequency of the light shouldn't make any difference. And the electrons, when they come off, they should have more energy if you have a brighter light, but it shouldn't matter if you change the color of the light. And it turned out that none of those things are true. They all have problems with them. And we can demonstrate. I need a volunteer to help me demonstrate that at least one of them is false. What's your name? Drew. Drew?
Yep.
OK, so what we're going to do here, I'm going to put some more electrons on this thing. And Drew is going to help me. I have a little aperture here. I can close and open the shutter. And as I close and open the shutter, that's going to let more light onto the thing. And so this will be able to tell if I get more charge coming off, more electrons coming off by increasing the intensity in this case. So Drew's going to hold this right in front of this, and you've got to be careful not to touch the metal of it. So I'm going to let you come on this side. And I'm going to put this little piece of glass here so to make sure we don't actually touch it. So let's, hang on. So I need this to come right in there. Okay? Okay, so now, okay, nothing's happening. Okay, so now I'm going to open the aperture. I'm going to let more intensity onto the thing. The aperture's opening. The aperture's opening. And I still don't, do you agree the aperture's all the way open? Whoop. Sorry. Right. So it does help if I have the light on. It's always a... Okay, so now we have a small aperture. I'm going to open the aperture. I'm getting more and more light on the thing. Now you agree there's a lot of light, yes? Yeah. But look, nothing's happening. The thing's not moving. I've increased the intensity, but I'm not getting any current coming off. Oh, something's a little different than what I did before. I had this piece of glass in. When I remove the piece of glass, now the things come together. If I put the piece of glass on, they stop. If I take the piece of glass away, they come together. So what's going on? Does anyone have any idea what this piece of glass is doing? He says that it's interfering with the light waves. In particular, glass does not transmit ultraviolet light. It only transmits visible light. It doesn't transmit ultraviolet. So what we've seen, can I do this the right way? Yeah, okay. Thanks very much. And just for playing along, a lovely Einstein mug. Okay, so what that showed was that changing the intensity in this case didn't necessarily have an effect, but changing the frequency did have an effect. Putting light of a different color on the metal did change whether or not electrons were coming off of it. So Einstein's explanation for this was that light was not coming as a wave. It was instead coming in discrete little packets, which we would call photons. And the energy of those photons was related to the wavelength of the light or to the frequency of the light by this constant called Planck's constant, a very small number. And I'm just going to show now what Einstein's model of this would look like. So here's my electron and my metal, and here are photons that don't have much energy. So I can increase the intensity by having more of them, but they don't have enough to liberate the electron. And here's a photon that has a little more energy. It's, instead of infrared, it's, say, a red photon, and it has just sort of enough to liberate the electron. And here's a nice ultraviolet photon that has a lot of energy, and when I put that on, now it knocks the electron right off and gives it lots of kinetic energy. So this is the model then that Einstein has of the photoelectric effect, which completely explains it and makes lots of other predictions about that. Now, even so, Einstein's paper was all about the fact that light is coming as particles, and yet people just had a really hard time accepting that light could be particles because they saw the Croissant Spot. They saw that it had to be waves. And so when he made this prediction, people had some things to say about it. So Max Planck, the guy who the Planck's constant is named after, he said that describing Einstein, sometimes when he's describing, for example, light quanta, he may have gone overboard, but we shouldn't hold that against him. Niels Bohr, who's one of the people who discussed how we can get atoms out of the quantum mechanics, said that light quanta is not able to throw light, pardon the pun, on the nature of radiation. Millikan, who discovered the electron charge, said that Einstein's paper is bold, maybe even reckless, and flies completely in the face of what we know in terms of interference. And then Millikan went and did the photoelectric effect just as Einstein predicted, said he should, got exactly the same results that Einstein said he would, and he said it's unambiguous experimental verification in spite of its unreasonableness, since it seems to violate everything we know about the interference of light. So people basically, for 10, 15 years after Einstein proposed this, still didn't believe that light was coming in photons. They finally did eventually, but it didn't happen immediately. Now we definitely know that that's the case, though. And in fact, the photoelectric effect has lots of practical applications. Various photodetectors all rely on that. The fact that when you shine light on things, you can excite the electrons out of them, and then you can detect light that way. Metals, it turns out, need, say, ultraviolet light for that to happen. But if instead you use semiconductors, they can see light that has much less energy. And in fact, I wanted to just show you a cute trick you can do at home. How many people have a digital camera? OK, almost everyone has digital cameras these days. So if we let me use, I'm going to use the other demo instead, Michelson. OK, so what I have here is an ordinary remote control. I don't know what it's a remote control for. I'm not going to hit all the buttons because I don't want to have the roof start coming down on me. But it's a normal remote control. And if I hit, for example, this volume button, you know, what? I'm hitting the volume button. What do you see? Nothing. You don't see anything, right? This is a normal remote control like your TV remote or like your remote at for your stereo or something. And now I'm just going to stand here and I'm going to hit the volume button instead. And I hope you see something, yes? Am I in the right camera? OK, so you see these flashing LEDs that are coming out of it. It's because it's emitting in the infrared. It's not emitting in the visible. You can't see visible with your eye, but it turns out all your digital cameras can see infrared really easily. So you can go and look and see what kind of pattern comes out. Depending on which button you hit, you can actually get different kind of patterns sometimes coming out of the different sources. And you can see all those with your infrared camera. And it's basically because of the photoelectric effect, because when photons come in, they can excite the electrons, and then those can be detected. And that's, of course, critical for making digital cameras and all other kinds of things, barcode scanners, solar cells, all things in our technologies that we use all the time. So Einstein called this his revolutionary idea. I'm going to wrap up in just a couple minutes here. So one of the consequences that happened a few years later, when people finally believed that light was actually particles, was one of them, Louis de Broglie, said, well, if Einstein says that light is, which we all knew was a wave, is really particles, maybe everything that we really think of as particles are really waves, or at least they can behave like they're waves. And that was, in some sense, the key idea of quantum mechanics, that Einstein said that photons have momentum, and you can get their momentum from their wavelength from this. And de Broglie said, well, maybe everything that has momentum actually has a wavelength. Now, my wavelength, if I'm walking at, say, a meter per second, is this 10 to the minus 35 meters, something really, really small. So you'd never be able to detect it. If you have an electron, say, in a television set, that will have a wavelength that's maybe 10 to the minus 10 meters, which is very small, but not so small that you can't actually observe it. And I'm going to do a demo now to show you, in fact, that light has, that electrons have a wavelength. So if I want to prove that electrons behave like waves, what do I need to do? What do we need to see? I need to see some kind of interference. OK, so I need to switch cameras. OK, so I've already showed you when light hits a little black disk, what we see. We get a little bright spot in the middle. If instead I send light through a little hole, this is light going through a hole, then I get this pattern of rings, this diffraction pattern of rings. So this is a typical interference pattern of light going through a circular aperture. And now I want to do exactly the same thing with electrons instead of with light. And so what I have here is a little electron gun, and the electrons are accelerated. Let me just draw a brief picture of this. So I have electrons which are shooting off here, and the electrons are passed through a tiny hole, and then I have a phosphorus screen here, and when an electron hits the screen, then it gives off a photon, or multiple photons, probably just one, I guess, and then we'll see whether or not we get an interference pattern. So if electrons are acting just like particles, all I'll get is the shadow of the hole. I'll just get sort of a disk. But what we see instead is I get these rings. So there's a ring here. There's a ring out here. If I give the electrons a little bit less energy, they have a little bit less momentum. That gives them a longer wavelength. And then they actually diffract a little bit more. So as I lower the energy, these rings actually move out a little bit. You can maybe see them moving out as I do this. So this is a demonstration of the fact that the electrons are acting like waves. The electron is sort of, well, it's interfering with itself. It's existing over this whole ring at a time. Very strange things, this quantum mechanics stuff. In fact, Einstein didn't really like quantum mechanics, although he sort of introduced it. He didn't like the fact that it was probabilistic. We couldn't actually predict in this experiment where any given electron is going to go. It's completely random whether an electron is going to go here, or whether it would show up here, or whether it would show up here. And that was a strange thing of quantum mechanics. Classical physics would say as long as you knew how it started, you could always predict exactly what was going to happen. Like this tennis ball, if I knew exactly how it started, I could predict a second later exactly where it was going to be. And yet with quantum mechanics, that wasn't the case. And that led Einstein to say that God does not play dice with the universe. And it was in 1916 that Einstein finally came up with the general theory of relativity. So the special theory of relativity dealt with light and dealt with people who were moving with respect to each other. The general theory of relativity had to deal with gravity and the fact that mass somehow actually warps space-time. And people, again, this is sort of in the collective consciousness. The idea is that if this is representing space or space-time and I have a heavy object, that actually warps the space. And then if I have another, so this is like the sun sitting at the middle. If I have the Earth going around here, well, it feels that curvature in space and then it orbits around the sun. And hopefully doesn't like crash into it like it did right there. Okay, so people sort of know this. Now, Einstein, when he originally applied this to the universe, he had kind of a problem. Things didn't really work out the way he wanted them to, and I need another helper for this. So I just need you to stand here and hold this and maybe rotate around this way. And the problem is this. When Einstein's trying to solve for how the universe might go, how the mass in the universe might go, he said, well, let's say I just put a bunch of masses all over the universe in sort of random places. And the problem is that when I do that, okay, I want to start them all at once, and then I let them go, they always curve space, and so they always collapse in on each other. And so everything always, you can't get a stable configuration. And yet as you look out into the universe, all the mass of the universe isn't all clumped together. It's out there. It's out there in the universe. And no matter how you start this, you always end up with the problem that things come together. So how could I keep these things from coming together? What might I do to this? Yes? So that's one idea, is that they could be moving. We'll come to that in a minute. Pardon? Right, so gravity is what's pulling them in. No, I think you're in a good space, yes? If the red area were somehow getting bigger, if I were changing it, Einstein actually had a simpler idea, which I'm sort of, which is that if I could keep these things from moving in, if I had some other thing underneath which was sort of expanding it. So if instead of this starting out flat, it was sort of being pushed up, if it was being bellowed up, then that would be some kind of a pressure that would keep things from coming in. And Einstein called that the cosmological constant. And what's your name?
Matt.
Yes, Matt. Of course, I know. Thank you very much for your help. And
Thank you, Professor.
a T-shirt also. Okay, so Einstein, that was a cosmological constant. It was a way that you could make all the mass go in the universe with having it all come together. And then it was discovered pretty soon thereafter that, in fact, all the mass in the universe, the galaxies are all traveling away from each other, as someone said. And Einstein said, oh, that was stupid of me. I didn't think about the fact that it could have been moving, and if it's moving away from each other, then I don't need to have this cosmological constant. And he called that the greatest blunder of his career, the greatest mistake of his career. Okay, the reason I bring that up is that now we know, as of several years ago, that we know that the universe is expanding. Okay, we've known that for a long time. It's getting bigger, but it's worse than that. It's actually accelerating away from us. So if you look at faraway galaxies, they're actually accelerating. Why is that kind of strange? So imagine that this little toad is the universe. And you could sort of imagine there's a big bang where the universe goes up, and if it doesn't go up very fast, eventually it stops expanding and then it comes together. Or you could throw this really hard so that it has escape velocity, and then things keep moving apart. Or, that may be just on the borderline. But in all of these cases, if you imagine this going away from the Earth, it's still going to be slowing down because it's always attracted back to the Earth, right? Because there's always a gravitational attraction back to the Earth. But what we see in the universe now as we look out is that the faraway galaxies things are actually speeding up. They're getting faster. So that's really strange. And to explain that, people have introduced the term dark energy. But we don't really know what dark energy is. We know that it makes up about 70% of the universe, so 2/3 of the universe. We don't have any idea what it is. But it's basically a type of, or one example of, a cosmological constant. It's something which is keeping the universe expanding. So even what Einstein thought was his greatest mistake, his greatest blunder, has a very high chance that it's actually correct now and that we need to go back to it. Okay, so just to summarize, in this miracle year, light is coming in pieces, quanta, photons, that basically started all of quantum mechanics. His senior thesis, which he then published, was looking at sizes of atoms using sugar solutions, and that led then to this Brownian Motion paper that we've discussed. This whole new way of thinking about motion and time and space with special relativity, and finally then the relationship between energy and mass, all in 5 years, all while Einstein was not at a university. He was a patent clerk. He was not in close contact with lots and lots of scientists. He didn't have lots of information coming in. He was basically doing all of these kinds of things on his own, and therefore it's perhaps no wonder that Einstein was voted the person of the century by Time magazine and by lots of other things. He basically started all of modern statistical physics, or proving it, special relativity, quantum mechanics. In some ways can all be traced back to Einstein and to that one critical year. Okay, so I have just, he was a little bit of a humble person, yes? So I thank you very much for your attention, and I'm happy to answer any questions you may have.